All right, problem 4 on the calculator side of things. The half-life of a radioactive plutonium-234 is 9 hours. If 80 milligrams is present now, I don't know. If 80 milligrams are present now, how long until only 15 milligrams are present? That seems inconsistent. I think it should be R and R. Whatever, that is irrelevant to the problem. Let's talk about how we're going to solve this problem. Well, to solve this, we're going to need to use our exponential growth / decay model, which is P of t equals P naught times e to the power of k t. And let's talk about what these things mean. P of t is saying the population size after time t. P naught, that little P naught right there, that is saying the initial population size, so the population at time 0. E is the natural number. It is a number like pi, the natural number e. So that is a constant. It's a button on your calculator, just like pi is a button on your calculator. K is going to be our rate. That's going to be our rate of growth or decay, depending on the problem. And then finally, T is, predictably, the time, and the units of time are going to be the same as the units of time on the P of t right there. So we're told the half-life of radioactive plutonium is 9 hours. So our time units are going to be hours. And how do we use this? Well, if 80 milligrams are present now, how long until only 15 milligrams are present? In order to do this problem, we're going to need to figure out K, our rate of growth. We know the initial population size. We know the natural number E. It's a constant. We don't know the rate of growth, and we don't know time. So we need to figure one of those things out so that we can solve for the other, which means we need to figure out our rate of growth using the half-life time. So how are we going to do that? Well, let's talk about half-life. Half-life means it's the amount of time it takes until half of what you started with remains. So for initial population size, let's imagine that we started with just, let's say we started with 2 milligrams of our substance. I know we didn't, but let's say we did. Let's say we started with 2 milligrams of our substance, then our equation would be 2 times e to the power of k. Still don't know k, but let's allow t, the time, to be the half-life, 9 hours. Now if I do that, what do I need to put on the left? Well, the population size after time t. Well, what's going to be the size of the population after time t if 9 hours have passed? Well, if 9 hours have passed, that is the half-life, which means half of what I've started with remains. So if I started with 2, after 9 hours, I'm left with 1. So I can get an equation like this. 1 equals 2 times e to the k times 9. And what do? Well, I want to get k. K is an exponent. This means I need to use logs. So in order to get k down, I first need to isolate this bit, which means I need to divide by 2. And so let's divide by 2 on both sides, and I get 1/2 equals e to the power of k times 9. Okay, so hopefully you see it is totally irrelevant that I started with 2 when I wrote this equation. I could have started with 10 instead of the 2, but that means I would have had to put 5 on the left side of the equation because 5 is half of 2, half of 10. No matter what you put as that starting, you need to have half of it on the left if your time is the half-life. It will always work out to say half equals e to the k times the half-life. So let's keep going. At this stage, I could rewrite things. I could take, notice the on the right side, my exponential bit has a base of e. So I could do a log base e on both sides. And what that's going to work out to giving me is a log base e of 1/2 equals k times 9. And that's, again, just rewriting it from an exponential form, rewriting it in logarithmic form. So I've got log base e, which is commonly written as ln. It's the natural log. So I have the natural log of 1/2 equals k times 9, but I want k, not k times 9, so I need to divide by 9. So I get the natural log of 1/2 divided by 9 will tell me k, my rate of decay. So figure out what that is on your calculator. Notice your calculator has a natural log button right here. So hit that natural log button, type 1/2, close the parenthesis, divide it by 9, hit enter. You're going to get a really nasty decimal. You're going to get that k is roughly negative 0.077016354 gross nastiness, and it goes on forever. Now what I want you to do is I want you to store that number as a variable. So after you type in ln of 1/2 divided by 9 and get that gross number, hit the store button, which is the button right below the ln button. Do that, and on your screen it should say A and S for answer, and then it should have an arrow like that indicating that you want to store that answer. Now we want to store that answer to a variable. So if you hit the alpha button and then the math button, it will store that to variable A once you hit enter. So go ahead and store that to A, and now that exact value is stored and we can use it in our future calculations. Because we are not done with this problem, all we've done is find the rate of decay. And I know it's decay because it is a negative number, so it is decaying what I'm doing. So let's look back at that original problem now that we know our rate of decay. We want to know if we start with 80 milligrams, how long until only 15 milligrams are present. So let's use our model here. We want 15 milligrams to remain, which means we need 15 equals the starting population of 80 times e to the power of our rate, which we just stored as a. So I'm going to write that as an a, but know that it's actually that number now. Let's make that actually look like an a. That is our, our rate, and that gets multiplied by time. Now, it looks like I have 3 variables in this, but I don't, right? E is the natural number e. That's not a variable. It's a button on our calculator. A is the stored value of our rate of decay. So that is also not a variable. The only unknown here is t. That's what we want. So how do we find it? Well, it's an exponent, so we use logs. So we need to take 15 and divide it by 80, because that will give us just the exponential part. And now if we natural log both sides, the natural log of 15 over 80, AD, has to equal A times T. That is rewriting it in logarithmic form. If you don't see that, think about it like this. The natural log of 15 over 80 equals the natural log of e to the at. Well, you could plug it and bring the at down in front, and the natural log of e is just 1, because natural log is base e. So it's saying e to what power is e? Well, e to the first is e. So either way, we get this equation right here. We want t, so we divide by a. So ln of, on your calculator, 15 divided by 80. Close your parenthesis, and then divide that by a. And to get a, you have to hit alpha math, but it'll give it to you, and it will tell you that t is, if we round it, 21.735 hours are the units we are using. So 21.735 hours should be our answer. Now, if you did not store that variable and you did the natural log of 15 over 80 divided by negative 0.077, like that, rounding that growth rate, you would get an answer of 21.734, which is, I will agree, very, 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 wait, I did that wrong. You would get 21.74, which is very close, right? You're off by 5 thousandths. It's not a lot, but it is off, and depending on the actual application you're doing here, that could be significant. And so, if you don't round, you will get most of the credit, but you will not get full credit. To get full credit on this problem, you have to store that variable and give me that exact value, only rounding on that final step.